An air-cooled condenser is a type of heat exchanger used in refrigeration systems to reject heat from the refrigerant into the ambient air without the assistance of water. It accomplishes this by circulating the hot, high-pressure refrigerant from the compressor through a coil system, where heat is dissipated to the surrounding air with the aid of fans. Air-cooled condensers are extensively used in residential and commercial refrigeration and air conditioning systems because they offer a simple and efficient solution for heat rejection without the need for water or additional cooling mediums. The second law of thermodynamics teaches us that heat only flows from a higher temperature to a lower temperature. Therefore, in order to use an air-cooled condenser, the refrigerant condensing temperature must exceed the ambient dry bulb temperature. This is problematic for certain refrigerants that have high theoretical discharge temperatures. Ammonia, for example, has a theoretical discharge temperature of 179.8 degrees Fahrenheit when operating at a 20 degree Fahrenheit evaporator and 86 degree Fahrenheit condensing temperature. In order to use an air-cooled system in this circumstance, the ambient temperature must be several degrees less than 86 degrees Fahrenheit. As the ambient temperature rises, the condensing temperature will also be forced upward, which will result in unacceptably high discharge temperatures that will wreak havoc on the system. Because of this, ammonia systems have traditionally used evaporative or water-cooled condensers, and air-cooled condensers are most often applied in systems using halocarbon refrigerants which have lower discharge temperatures. The primary components in an air-cooled condenser are: each condenser will have at least one inlet connection to receive superheated vapor and one outlet connection where liquid exits the condenser. The refrigerant flows through a series of heat exchange coils made of copper in halocarbon systems or various steels for ammonia systems. Thin metal fins are attached to the coils to maximize the surface area in contact with the air, enhancing the heat transfer process. These coils and fins provide the necessary surface area for effective heat transfer. Fans move ambient air across the coils, facilitating heat dissipation from the refrigerant. The condenser is encased in a protective housing that supports the coil and fan assembly, often designed to optimize airflow and protect the components from environmental elements. The advantages for air-cooled condensers are fairly straightforward. First, air-cooled condensers do not require water. This is ideal in areas with limited water availability or where water conservation is a priority. Second, without the need for water, issues like scaling, corrosion, and water treatment are eliminated, reducing maintenance costs and complexity. Third, air-cooled condensers are less expensive and simpler to install compared to water and evaporatively cooled condensers. Before employing an air-cooled condenser in a refrigeration system, one must be aware of its drawbacks. First, the performance of air-cooled condensers is influenced by the ambient air temperature. In hot climates, their efficiency will decrease. Second, compared to water and evaporatively cooled condensers, air-cooled units may require more energy to reject the same amount of heat. Third, the fans used to move air across the coils can generate significant noise, which may be a concern in residential or noise-sensitive environments. To summarize, air-cooled condensers provide a reliable and cost-effective solution for heat rejection in refrigeration systems. Their water-free operation, low maintenance requirements, and versatility make them a popular choice across residential, commercial, and light industrial applications. However, water and evaporatively cooled systems offer higher efficiencies and are more widely used in large industrial systems, especially when ammonia is the refrigerant.
All right, now that we've been introduced to the three different types of condensers, let's just do a recap by summarizing the pros and cons of each. Okay, when we talk about an air-cooled condenser, that's the simplest of all of our condensers, and that is its advantage. Simplicity. Simplicity is a great thing. When we can go simple, let's not have any water, let's not have any pumps, let's not have any chemical water treatment. That's great, and that's what that air-cooled condenser provides to us. Unfortunately, the downside is it's going to result in higher discharge temperatures, a little more electricity costs, generally speaking, and especially when it comes to ammonia refrigeration, that's a problem because of ammonia's high theoretical discharge temperatures. Okay, the fluid cooling condenser situation is an upgrade to the air-cooled as it relates to energy costs, meaning we're going to operate a more efficient system by going fluid cooling, but unfortunately we've added complexity to our system because we now have a cooling tower, closed circuit cooler, we've got a heat exchanger, we've got pumps, that means we've got pipes connecting the components to one another, so we've increased complexity. Furthermore, we will have a maintenance burden and a cost burden as it relates to taking care of our tower, cleaning it, treating the water inside the unit as well. But it is a more common approach, especially for ammonia refrigeration, because it allows us to bring down our discharge pressure. And then the evap condenser is basically the best of both worlds because we're using air, we're using water, and by combining both those together, we actually get the most efficient operation. Another really cool advantage of the evap condenser is for situations where air-cooled works, an evap condenser can be operated as an air-cooled condenser. You can drain it of water, clean it out, and just run the fans. In a real cold climate or situation where air would work, evap can double as an air-cooled condenser. But nothing's perfect. Evap condensers do require a lot of maintenance. The sump, the water gets dirty, has to be cleaned. Of course, there's chemical treatment. There's safety concerns. A lot of times to enter the condenser is treated as a confined space. So there's no perfect solution when comparing the three different types of condensers. Pros and cons of each. So that provides that big overview for you.